The browning of white adipose tissue, the conversion of energy-storing white fat cells into energy-burning beige or brown-like fat cells, has become a central target in anti-obesity and metabolic health research. This transformation is associated with increased mitochondrial content, upregulation of thermogenic genes, notably UCP1, and greater oxidative capacity, allowing for enhanced energy expenditure. While cold exposure and certain hormones like irisin or norepinephrine are well-known triggers of fat browning, recent evidence suggests that autophagy, particularly mitochondrial remodeling via mitophagy, plays a critical role in this process. Nicotinamide mononucleotide (NMN), a precursor to NAD+, has emerged as a promising modulator of adipose tissue biology, capable of promoting white fat browning through autophagy-dependent mechanisms rooted in mitochondrial turnover and rejuvenation. White adipose tissue, WAT, in aging individuals typically becomes metabolically inert, storing excess calories and secreting pro-inflammatory cytokines that exacerbate insulin resistance. In contrast, beige adipocytes, cells within WAT depots that acquire thermogenic properties, contain a higher density of mitochondria and exhibit features similar to brown fat. One of the keys to this phenotypic shift is mitochondrial remodeling, the breakdown of dysfunctional mitochondria and the biogenesis of new, energetically efficient ones. This is where autophagy, particularly mitophagy, becomes crucial. Cells must clear out old mitochondria before producing new, functional ones capable of supporting high levels of oxidative phosphorylation and thermogenesis. NMN supports this transition at multiple levels, beginning with its elevation of NAD+ levels in adipose tissue. NAD+ is an essential cofactor for sirtuins, specifically SIRT1 and SIRT3, which regulate both autophagy and mitochondrial biogenesis. SIRT1, through deacetylation of autophagy-related proteins, such as ATG5, ATG7, and LC3, facilitates the formation and maturation of autophagosomes. It also activates PGC-1A, the master regulator of mitochondrial biogenesis and oxidative metabolism. SIRT3, localized in the mitochondria, enhances the efficiency of the electron transport chain and detoxifies reactive oxygen species by activating enzymes such as SOD2. Together, these sirtuins promote a cycle of mitochondrial cleanup and renewal essential for the emergence of beige fat cells. By activating SIRT1 and SIRT3, NMN effectively primes adipocytes for a shift from energy storage to energy expenditure. Autophagic flux is increased, allowing damaged mitochondria to be selectively removed. This relieves cells of metabolic stress and prepares the mitochondrial network for reprogramming. Concurrently, the stimulation of PGC-1A and thermogenic genes such as UCP1, CIDIA, and PRDM16 begins to reshape the cellular identity of adipocytes. The outcome is not just a cleaner, healthier cell, but one that is fundamentally more metabolically active and capable of thermogenesis. Rodent studies support this model. In aged or diet-induced obese mice, NMN supplementation has been shown to increase UCP1 expression and mitochondrial content in subcutaneous, white fat depots. These changes are often accompanied by elevated markers of autophagy, like LC3-2 and Beclin-1, increased NAD+ levels, and improved systemic metabolic parameters, including reduced fasting glucose and enhanced insulin sensitivity. Importantly, when autophagy is genetically impaired, such as through the deletion of key autophagy genes, these browning and metabolic benefits of NMN are significantly blunted. This strongly suggests that NMN's capacity to induce white fat browning is autophagy-dependent and tightly linked to mitochondrial turnover. The implications of this mechanism are far-reaching. By facilitating the conversion of white fat into thermogenically competent beige fat, NMN could help shift the energy balance in aging individuals from storage to expenditure, potentially reversing age-related fat accumulation and metabolic inertia. Unlike stimulants or pharmacologic uncouplers that increase energy expenditure by forcing the system, NMN operates by restoring intrinsic cellular capacity, reactivating the cell's natural processes of renewal, adaptation, and energy regulation. Furthermore, NMN's browning effect may not be limited to just one depot. Some studies suggest that visceral fat, long considered metabolically detrimental, may also exhibit partial beiging under NMN treatment when autophagy is engaged. While this area requires more research, the idea that NMN can influence multiple fat reservoirs through a unified mechanism involving mitochondrial autophagy is compelling. In conclusion, NMN promotes the browning of white adipose tissue by enhancing autophagy, particularly mitophagy, and driving mitochondrial remodeling. This process not only clears dysfunctional components, but also enables a functional transformation of the adipocyte into a more oxidative, energy-expending cell. Through this pathway, NMN holds significant promise in combating age-related weight gain, metabolic inflexibility, and fat-driven inflammation, not by acting as a thermogenic drug, but by reigniting the cell's own regenerative machinery. As research into NMN and adipose biology advances, its role as a metabolic reprogramming agent, particularly through autophagy, may become a cornerstone in the fight against metabolic disease and age-related obesity.